Hi, my name is Anjali, and I'm super excited to tell you about my 109 project where I built a randomized probabilistic algorithm for decrypting monoalphabetic substitution ciphertext. So, what does that mean? My algorithm takes in as input text where every letter in that ciphertext maps back to some other letter, A through Z, in the original plaintext. And my algorithm's job is to find that encryption key mapping so we can successfully decrypt the text. So, as an example, I've chosen a passage here to kill a mockingbird. And what I'm going to do just to understand the input to our algorithm is generate some random encryption key mapping and let's just encrypt the text. So if I run this guy right here, we can see that something like this is what my algorithm takes in as input, an encrypted passage where it doesn't know the encryption key mapping, and the algorithm's job is to figure out what that mapping is, and then use that ideally correct mapping to successfully decrypt the text. So the algorithm is running. This might be where Chris plays take five. Almost done. The wheels are turning. And we can see here it did work. And here's how we know. The algorithm had 100% decryption accuracy, a score of 1.0. This was the encryption key prediction. And if we look at this passage, it is the exact same as our original input passage. Yay! So how did the algorithm work? Well, this plot right here can help us think about the algorithm sort of similar to gradient ascent and hilltop climbing. Just like we were trying to find the parameters that best matched our data in gradient ascent, here we're trying to find the encryption key of our 26 factorial size search space. That we were trying to find the correct one that maximizes the likelihood of the decrypted passage in terms of the English language. So my algorithm starts off with a prior belief of the encryption key that I assign based on the frequency of letters in the ciphertext and how those relate to the most common letters in the English language. And across the many iterations, you saw that I printed a lot of numbers in the terminal as the algorithm ran. It was one per iteration. So across these 8,000 iterations, the algorithm's guess, the algorithm's current belief of the encryption key becomes better and better and better, working towards that global optima, this dashed line. So this dashed line here represents the likelihood of seeing our encrypted passage when decrypted with the correct key. So at each step of the algorithm, we decrypt the passage according to our current key belief and look at the likelihood of that decryption text, continually trying to improve. So for a bit more of a technical understanding in terms of how we actually explore this encryption key sample space, we start off with some prior belief. And then across our iterations, we always formulate our next key to explore by randomly swapping any two mapping values in our current encryption key guess. We then compute the log likelihood of our encrypted text when decrypted under that new key belief. And then we see two cases. The first case is if that new key gave us a better likelihood than our existing belief, we're going to update our existing belief. We found a better key that's getting us closer to that global optima. Otherwise, we accept the new key, even though it had a smaller likelihood, with a probability that we define here as the acceptance probability. We do a Bernoulli coin flip, and if it is successful within that acceptance probability, then we still update our key belief. For more insight here, please see my paper, but the main idea behind this logic is we're giving the algorithm a chance to get over being stuck at local optima and still find that tallest hilltop. Maybe one more example I can show you is when the algorithm doesn't do so well. So I found that for New York Times politics, that's one example where the algorithm struggles a bit. And as we run it, I will show you why I think that is. So I noticed that in cases where the algorithm struggles, there's a lot of proper nouns here: Mark Zuckerberg, Donald Trump, Palm Beach, it goes on and on. And these words are not commonly recognized as the most frequent English words that my algorithm rewards when calculating the likelihood of. So I found that my algorithm is biased towards words that do occur frequently in English. So we can see here it converged not at the global optima. It got stuck at a local optima, and that is a place for future improvement. Overall, though, I think the algorithm shows great promise in being able to explore local optima and find a global optima among a massive size search space, especially when there are common English words and we give a long enough size passage. And I look forward to continue iterating from here. Thank you.